Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present viscosity of epoxy resins. We all have an understanding of the viscosity of a fluid. For example, we know honey is more viscous than water. Viscosity is a measure of fluid's resistance to flow. Viscous fluids feel thicker. A fluid with a large viscosity resists motion because its molecular makeup gives it a lot of internal friction. A fluid with low viscosity flows easily because its molecules makeup results in very little friction when it is in motion. What are the factors affecting the viscosity of epoxy resins? Temperature. Increases in temperature results in a viscosity decrease. Degree of cure. By an increase in the degree of cross-linking, the viscosity is increased. The addition of resin fillers and tougheners increasing the particulate content and so results in a viscosity increase. Finally, the use of diluents and solvents for viscosity reduction is a common practice to reduce the viscosities in epoxies. To explain viscosity, we have to start with a fluid flow over a flat surface. We can imagine that fluid flows in different plates with different velocities. Look at this figure on the right for this notion. Due to the presence of different velocities between the planes, we have a shear between them. It works as friction between different solid objects. The maximum shear is at the wall as we have no slip conditions, meaning that the fluid is stagnant right at the surface. And far from the surface, the fluid layer cannot feel the wall at all. The slope of this curve changes and it is large near the surface. It shows by changing the distance, the velocity changes substantially. If we plot the profile of a velocity u versus distance from the wall, we would have this image on left. For most fluids, the relationship between the shear stress and the slope of velocity is linear. The slope of this curve is called viscosity. The explained relationship can be expressed based on this equation, which is called Newton's law of viscosity. And this mu is called dynamic viscosity. We also can define kinematic viscosity, which is the dynamic viscosity over density. See the equation on the right side of the screen. Dynamic viscosity has the unit of Pascal per second, and kinematic viscosity has the unit of meter square per second. The poise and Stokes are other units in use. However, often we use centipoises and centistokes. So again, we have dynamic viscosity, which has a dimension of poise. The equation presented at left, which is depicted by mu. And also we have kinematic viscosity with a dimension of Stokes, presented on the right and depicted by nu. So we said that the centipoises as the measure of the dynamic viscosity. Now let's look at the viscosity of different well-known fluids to get an idea about the feel of this concept, as well as the magnitude of centipoise. Starting with water, which is known to have a viscosity of 1 centipoise. blood, how thick it is, has a viscosity of 10 centipoise. The mu is around 500 centipoise for various oils, and for honey at 25 centigrade it is about 7,500 centipoise. For bitumen it is around 700,000 centipoise. Fluids that obey Newtonian's law of viscosity are said to be Newtonian, which means that the shear stress increases linearly with the strain rates. But this is not the case for all fluids. We also have shear-thickening fluids and shear-thinning fluids. These are called non-Newtonian fluids, as they cannot be explained based on Newtonian's law. For shear-thickening fluids, the apparent viscosity increases as the strain rate increases. And for shear-thinning fluids, the apparent viscosity reduces as the strain rate increases. Paint is an example of a shear-thinning product. The viscosity is high when the shear rate is small, for example, when a brush is used to wet a surface. It is not dripping when, for example, you are trying to wet the surface. However, it is about to be applied on a wall. When it is about to be applied on a wall and the shear is increased, the viscosity is reduced, which facilitates the brushing process. It's also believed that the epoxy behaves in a shear-thinning manner. There are different units that exist for reporting the viscosity. We already mentioned that if you divide the dynamic viscosity by the density, you would have the kinematic viscosity. If you have the Piose value of the viscosity of a resin or fluid, if you multiply this number by this factor, for example 100, you will have its centipoise value. If you multiply it by 6.9 multiplied by 10 to the power of 4, you would have it in Reyn dimension. If you need the stock value, you have to divide it by the density and so on. This table is a good guide to understanding and converting different viscosity values. We also can use these types of tables to simply convert different dynamic or kinematic viscosities in different dimensions to each other. These tables are pretty useful when the viscosities have been reported in different non-standard units. When you have the viscosity in pound second per square feet, you can use this table and obtain it in Pascal per second value. The same principle is also valid for kinematic viscosities in different dimensions. These type of tables can be found in different references. There are different methods exist to measure the viscosity. These methods can be applied to measure either the dynamic viscosity or the kinematic viscosity. Moreover, these methods can be used to measure the viscosity at a single point. For example, at a certain temperature or in a range of temperatures. The most common techniques to measure the viscosity include Orifice-Type Viscometers or Viscosity Cups, Vibrational Viscometers, Rotational Viscometers, Capillary Viscometers, U-tube Viscometers, and falling sphere Viscometers. Here we can see a schematic of the instruments used to measure viscosity. These methods will be briefly introduced in the subsequent slides. The capillary viscometer is one of the earliest known methods to determine fluid viscosity. This method measures the time taken for a defined volume of fluid to flow through a U-shaped capillary tube of known diameter and length. The tube usually has two marks, an upper and a lower mark, which are used as a measurement references. The time it takes for the fluid to flow past these marks is proportional to the kinematic viscosity. Capillary viscometers include the Ostwald and Ubbelohde viscometers. Both are U-shaped instruments, have two glass bulbs, and use capillary tubes. The key difference between Ostwald and Ubbelohde viscometers is that the Ostwald viscometer is suitable for measuring low to moderate viscosity liquids, whereas the Ubbelohde viscometer is suitable for measuring high viscosity liquids. One major advantage of Ubbelohde viscometer is that the values it obtains are independent of the total volume of the liquid used. The falling spherism viscometer is used to determine transparent Newtonian fluid viscosity. The concept involves measuring the time it takes for a sphere of known density to fall through a sample-filled tube, for example filled with liquid epoxy, under gravity. The tube is usually mounted on an apparatus that can quickly rotate at 118 degrees to allow repeating the test upside down. The average time of 3 tests are recorded and used in a conversion formula to determine the viscosity of the sample. The formula is shown here. L is the length of the tube, and rhos are densities of the ball and fluid. G is gravity, and T is the time. D stands for the diameter. The instruments contains various balls with various diameters suitable to be used for different fluids with different viscosity ranges. Falling sphere viscometers are used for quality control in various industries as well as in academic institutions to illustrate scientific method. The ease of use and a straightforward method for recording time measurements ensures meaningful test results. Viscosity cups are used to determine a fluid kinematic viscosity and are typically made of anodized aluminum with a stainless steel orifice. The cup is filled with the fluid and the orifice is placed at the bottom of the cup, where fluid can pass through. This relatively simple test involves placing the fluid in a container with a small opening at the bottom. The fluid is allowed to flow through the opening in a precise amount. The time it takes for the fluid to pass through the opening is measured and correlated to the viscosity through the use of charts applied for the given cup. Different cups are available and the most important ones are depicted here. ISO cups and Ford cups are the most common ones. We also have Zahn cups, Gardner-Fisher cups, and Easy cups. If the viscosity is measured based on these cups, often it is printed at the corresponding viscosity. Therefore, we may see Gardner viscosity, Ford viscosity, etc. in the TDS document, simply meaning that the viscosity has been measured based on that specific method. Here again, we have various nozzles for fluids with a range of viscosities. When the viscosity is higher, an orifice with a higher diameter is used. The time it takes for the flow of fluid through the nozzle can be pointed to choose the correct orifice. It simply has to be in the suitable range. If the time is so long, an orifice with a higher diameter has to be chosen. And if it takes just a few seconds for the fluid to pass through the nozzle, an orifice with a smaller diameter has to be used. In this slide, you can see a visual of a Ford cup viscometer. Pay attention to the orifice in the bottom, which can be replaced by another orifice with a higher or lower diameter. Therefore, in this type of viscosity measurement, the orifice is the heart of the measurement. As the volume is fixed and it is precisely known, the efflux time in seconds can be measured while the fluid is passing through the nozzle. This number can be converted to the viscosity units. Based on the type of the employed for the cup, for example, if it is number 1, number 2, or other. And with the measure of efflux time, we can use this chart to convert it into kinematic viscosity. We also can use the table to convert efflux time in seconds to viscosity in centistocks. If you heard of viscosity measured based on time, it simply means that it is efflux time. And if you ask about the type of cups employed, you can simply calculate the viscosity in the correct dimensions. Ford and Zahn cups are some of the most commonly used viscosity cup varieties. Each cup design is unique, thus care must be taken when comparing viscosity values between different cup types. The values a viscosity cup provides is an absolute value and does not include the allowed tolerances. The same principle applies to other cup type viscosity measurements. And tables or charts are provided by the supplier of the cup and should be used as references. Here, the design of various Zahn cups has been depicted for your reference. Again, here based on the viscosity expectations, a cup with proper nozzle size is chosen. The cup is filled with the resins to the marked known volume. The nozzle is then left open and the fluid flow through the nozzle. The time is measured until the drips of the fluid appear. This time is used in a similar way to calculate the viscosity. Properties of different Zahn cups have been shown here as well. Here an overview of all different cup designs and the formula to convert the time to the viscosity have been presented. It is a valuable source for your future reference. There are also times that a customer knows the acceptable viscosity which works fine for his or her system, but in different units. You provide the TDS of your product to a customer in which the viscosity has been presented in, let's say, centistocks, for example, which is the standard way. He needs or she needs to know what that means in Ford cup viscosity, for example. You have to change this viscosity to the unit he needs. In this situation, this type of charts can be employed. This table is also useful for converting different viscosities to each other. For example, if you use an ISO cup type 5 and fluid flows for 33 seconds, the viscosity is 102 centistocks. We also have other different Orifice-Type viscosity instruments which are used in the industry frequently. The principle here is almost the same as the former ones and concerns the time duration that a certain amount of fluid passes through an orifice with a known diameter. In the Saybolt or Redwood methods, the containers have a heating jacket that allows to conduct the viscosity measurements at various temperatures. By the way, here's the conversion tables to convert the centistocks, Redwood, or Saybolt viscosities. For example, if for a resin Redwood viscosity of 49 seconds has been reported, it simply means that the viscosity is 9 centistocks. Rotational viscometers work by measuring the torque required to rotate an object in the test fluid. In these methods, a cup or a container is filled with the fluid, a spindle is rotated in it, and the torque is measured and automatically converted to the dynamic viscosity. The torque maintaining the set speed is directly proportional to the viscosity. Therefore, the apparatus is capable of outputting viscosity, shear stress, and stress rate values. Because an external shear force is applied to this liquid, rotational viscometers measures the fluid's dynamic viscosity. Cup and bobs, cones, and plates are all types of rotational viscometers. Cup and bob viscometers consist of coaxial cylinders of different diameters. A volume of a sample to be sheared is stored within the test cells. The torque required to achieve a certain rotational speed is then measured and plotted. Cone and plate viscometers have a precise torque meter, which is driven as a discrete rotational speed. It uses narrow angle cone in close proximity to the flat plate. The viscosity is calculated from shear stress and shear rate. These methods are used often for non-Newtonian fluids. Different spindle shapes and geometries have been shown in this figure. The spindle can be simply detached and another spindle can be used in the Brookfield instrument. Different types of spindles are suitable for different fluids with different viscosities. The higher the viscosity of a sample, the smaller the spindle. Details and properties of these spindles are provided by the manufacturer. Different standards are published to measure and report the viscosity. The most important ones have been presented here. ISO 2884 is the determination of the viscosity using rotary viscometers. Part 1 discusses the cone and plates viscometer operated at high rate of shear. ISO 3104 is the standard used for transparent and opaque liquid. It presents determination of kinematic viscosity and calculation of dynamic viscosity. ISO 3105 gives specification and operation instruction for glass capillary viscometer, widely used for the determination of kinematic viscosity of petroleum products. ISO 12058 is based on the falling ball method. ISO 2431 is based on flow cup measurements. ASTM D1200 present the Ford cup viscosity measurements. ASTM D4287 is high shear viscosity and is a cone and plate method. ASTM D446.0.7 is the capillary based method. ASTM D8807 is the standard procedure for the Saybolt method. ASTM 5152, and this is the standard refers to the standard for ISO cup method. We also have BS 3900A7 1 and 2, illustrate the cone and plates viscometry and elaborates a disc and bowl viscometry. Thanks for your attention. I hope you find this video interesting. Please share your thoughts, comments, or questions, and I will come back to you soon.